Yep, there we go. All right, can everyone hear me on Zoom? Everyone's fine on Zoom? All right, everyone can hear me on Zoom. All right, that's good. All right, we'll get started with this introduction to machine learning algorithms. So we'll be covering over two different algorithms today. One of them is called linear regression. The other one's called logistic regression. They both have different purposes and they both kind of serve, they both are used in different contexts. So we'll kind of go over, so it's important to know how both of them work at a basic level. So that's what we'll be covering today. But before we get started with any sort of machine learning algorithm, we kind of need to define some basics about machine learning. So, hello? So the first thing to know, the first difference to know is the difference between supervised and unsupervised learning. So what supervised learning is, it's basically we have like a known data set and we know what the correct output should be. Okay. So it's kind of like, let's say like you're trying to predict the price of a house. So you know what the correct price of the house should be, and you have your data set with whatever like things that you're trying to calculate. Okay, so that's what supervised learning is. It's basically a problem where we know what the output should be. So even in supervised learning, there's kind of two different classifications. There's a regression and there's classification problems. So regression problems are basically where we're trying to predict the results within a continuous output. So what that means is that it's kind of like a function. So like given any input, we should be able to map it to an output value. Okay. So basically, for an example, like if given the size of a house, we need to try to predict the price. So obviously the size of a house can be anything. It can be like 10 meters square, which I don't know why you'd have a house that small, but or it can be 500 meters square, and we should be able to predict the price for any value. That's valid. Okay. The other type of supervised learning problem that machine learning engineers face is classification problems. So this is basically problems where we try to predict the results and put them in sort of different groups, or like kind of predict the outputs. So basically we can take like a patient's data and we can group it in certain classes. So whether a patient has cancer or not. Okay. I think someone's unmuted on Zoom. Maybe that's just me. All right. The second type of distinction of machine learning problems is unsupervised learning. So this is basically problems where we have little or no information on what the results should look like. So a common example of an unsupervised learning problem is known as customer segregation. So it's kind of like an example of this is actually your go-karts. You know how there's different types of go-karts. You can have your adults, your childs, your concessions, etc. So basically, the reason why they have that kind of stuff is because of I don't know, for whatever reasons they figured out that like a concession obviously uses the go-kart a bit more, so they kind of get more concession because it's kind of cheaper for them, but they travel more, so they like transit earns more money because of that. Adults don't travel as much, so like they're ones charged a bit higher, so stuff like that. So all of this kind of information is under unsupervised learning. So if you're given a data set, you don't really know what it should be grouped as. Okay. One of the other things about unsupervised learning is that there's no feedback mechanism, or there's no idea of how correct you are. So there could be multiple right answers to the problems basically. So like right now let's say it's us, right? We're technically classified as adults, or we could be concessions, right? There's no correct answer for us. So it's kind of like that. So this is kind of what we call an unsupervised learning problem. Okay. So that's kind of like the basics of the machine learning stuff. We'll go over the first algorithm, which is the simple linear regression. Okay. Simple linear regression, pretty simple. There's just some notation to take care of. So we say y hat is equal to h theta of x. This is equal to theta naught plus theta 1 x. Okay. So x is kind of like your input parameter or the data that you're given. Okay. Theta naught and theta 1 are kind of the parameters that you're trying to vary. And your y hat is like the predicted output. Be careful that in this case, there's a hat over the top of the y, because this is referring to the predicted output. The values that we get, the actual values that we get from our data set, that's what we call y. So there's no hat on top of it. So that's kind of like a distinction between the two things. If you actually look very closely at this equation, this kind of resembles your simple, linear regression, the y equals mx plus c, like a normal straight line equation, but it's just some of the variables have been changed around. And actually, if you think about it, drawing a straight line to like a data point or something, like I'm sure you've done that in like assessment or something in high school. It's pretty much just a linear regression problem. So like you're given a set of data, so you're given like experimental data, and you know what your experiment output should be, and you kind of try and draw a line to sort of fit the data best. So like the stuff you probably did in high school about drawing straight lines, that's like on 2D, like on 2-dimensional. So you're given like you have one input parameter that you're varying, and you have like one output. So the stuff we'll cover is kind of like what happens if you change multiple parameters. So we'll kind of discuss that a bit later. So simple linear regression, pretty straightforward, nothing too difficult. Okay. So the next important thing to know is that, let's say we choose a random value of theta 0 and theta 1. Okay, we have some random parameters that we've taken. So how do we know how right or wrong we are? Okay, so there's currently no way we have to measure how accurate the answer actually is, or like how close the line is to the data points. It's kind of easy in like, if you're looking at it in 2D and you're given like a set of data points, it's kind of easy. You can kind of just say, oh, this line looks like it's passing through the data points nicely. This one looks like it's not. This one looks like it's a bit worse. So like maybe a line that's like vertical is probably not a good idea for most data sets, something like that. You know, it's kind of obvious. You can kind of have a look and just tell whether a line is fitting the data well or not. But as we start to go into like multi-dimensional stuff, obviously you can't plot like 10 dimensions of data and stuff like that. So so like that idea doesn't help anymore. So this is where we come up with this, what we call this cost function. So this is basically a measure of how accurate our answers actually are. Okay. So we basically want to try and minimize our cost. Basically, it's kind of like an obvious sort of thing, but we just want to minimize this value as much as possible. So if you have a cost of 0, that's the best value we can have, because that means that your data set is perfectly. That means your parameters and like your the line that you drew is perfectly fitting the data points. If it's a cost function that's really high, that means like you've messed something up, and like either your data set can't be fitted with a straight line, or your like parameters are wrong. So this notation is not too hard. It seems kind of complicated right now, but we'll kind of go over an example of what this notation actually just means. Let's give you this m here that it's kind of in the numerator, denominator, and in the summation sign. This is the number of training examples there are. So if you have like 10 examples if you have like 10 examples, then m would be 10, something like that. Okay. This h of theta of xi, this is kind of what we saw before. If we look at the simple linear equation, but this is just like you have a certain x value that you're giving into the input. So it's like if you like from a function stuff, if you have y equals mx plus c and you give x a certain value, you get a certain value for y. So this is kind of what this h theta of xi specifically means. Okay. Xi in this case basically means this is like an ith training example. So if x is 1, that means this is the first example. If x is 2, that means it's the second example, etc. Y of I here just means it's the actual output. Okay. Because as we said before, this h theta of xi, this is kind of like what we're guessing the answer should be. This y of I is kind of like what the actual answer should be. Okay. So this h theta of xi minus yi is kind of a way of showing how far we actually are from the answer. If this answer is 0, so if this difference is 0, that means that we're exactly on the answer. Yes.
Could you incorporate that notation something like, so in the first example, we have n approaches infinity to indicate that it goes to infinity. This could you incorporate something like n approaches 200 to represent 200 iterations?
This is actually more so a cost for like one sort of trial run kind of thing. So like iterations here doesn't make sense kind of thing.
Okay.
So I'll explain what this means with an example, then I'll probably clarify things for you. So oh, wrong computer. Okay, let's say this is kind of our training data. Okay, so the orange points are kind of like data that we've been given, and this white line that we have drawn here, this is kind of like what we're guessing the output, or this is what we're guessing that the best line of best fit actually is. Okay, so the way to figure out the error or the cost function, as we said, was firstly find out the distances between the data point and your line, basically. Okay, so this is kind of like if we go this is kind of like this difference basically between your error and the actual answer. Next thing we do is we actually square this error, and the reason why we want to square this error is because we don't really care whether the point is above the line or below the line. All we care about is how far it is away from the line. Okay, if we don't do the squaring stuff, then points that are below the line will actually cancel out with the points that are above the line. And it'll kind of make it seem like the line is actually really fitting nicely when it's actually not. So that's kind of why we square the distances here, or like the difference between your predicted output and your actual output. So again, this is the formula is given. So for the 5, so we had 5 training examples here. So like the 5 data points we were given. So you just go 1 on like 2 times 5, and then you take each of the errors that we were given. So like this vertical distance is E1, E2, E3, E4, E5, and you just kind of square them up and then just add them together. Okay. So this is kind of like, and this is how normally it works. Even if we have like 200 examples or 200 data points, we kind of just go through each one and just sum a square and then sum the values for them. Okay, so that's kind of what the cost function is, and it's an important parameter. It's an important thing to know in all your algorithms, because of the fact that if your algorithm is actually doing what it's supposed to, so if as you're going through like the iterations of training your examples and as you're going through and training your machine learning models, what you should actually see is that the cost should actually go down. So basically that means that your predicted line is getting better and better slowly over time. If for some reason your line, if for some reason the cost function is actually increasing, so as let's say like your first iteration, the cost function is like 300, let's say, so it's pretty bad, okay? But then the next iteration you do, it's 299, 250, and it keeps dropping, that means you're doing something well. That means the algorithm is working very well. If for some reason you see that your cost function is like increasing, it's going from like 10, 20, 30, 40, 50, as you're going through the algorithm, that means that there's something wrong with the algorithm. So either that your parameters have been chosen incorrectly, or that it's not the right type of fit for this data. Okay, so it's actually this cost function is actually a good way to see how right you actually are, and if you're going actually in the right direction. And it's actually quite a lot of machine learning engineers and machine learning practitioners actually use this method to figure out if they're actually stepping in the right direction. Okay. The next thing to know is like this little illustration. It's kind of like this weird one, but it makes sense once I explain it makes sense once I'll explain what the algorithm actually is. Okay, so right now we have a way of knowing how correct we actually are, but we have no way of actually knowing what the parameters should be. Okay, so like for all we know, the parameters, like we could just guess parameters and just keep guessing, and like that could be like our best. That could be, we just figure out what the best. We can figure out which one of those guesses has the lowest cost, and like that could like pretty much just be like a way to figure it out. But there is actually a way to kind of figure out these parameters using like a common sense sort of idea. Okay, so before I explain to you what the actual algorithm actually is, I'll kind of go over the intuition behind, or the common sense behind the algorithm. So let's imagine you're stuck on a hill. All right, you've been on a hiking trip and you're lost. All right, you don't know where you are. It's getting kind of dark. It's getting foggy. Okay, and you're scared and you're alone in the forest and you want to get home. All right, you want to get to your home, and you know that your base camp, whatever. The thing you know about the base camp is that it's at the lowest point of the mountain. Okay, so wherever you are at your hiking trip, or like wherever you are on top of wherever you are on the mountain, the thing you know is that the base camp is at the lowest point on the mountain. Okay, so you can't really see which direction you should actually be going in. So what's the common sense thing to do is kind of see which way is downwards, like kind of look at the slope of like the mountain and see which way is downwards, right? And you can kind of just start stepping in the downwards direction slowly and slowly. And like common sense dictates that if you keep stepping in the downwards direction, common sense kind of dictates that eventually you should reach the bottom of the mountain. Okay. This is it's kind of like the idea behind this gradient descent algorithm. Okay, so it's kind of like we're descending, and yeah, all right. So that's kind of like the logic behind this, like the common sense intuition behind how this algorithm works. So basically, what you do is you take a step in a direction that you think is the lowest, like the steepest sloping downwards. Okay, then you stop, reevaluate, and then kind of see, look around you and kind of see, okay, maybe the direction I was going in initially isn't actually the best direction. Maybe I should be traveling this other direction. Okay, you take another step, stop, reevaluate your position. Again, figure out where the lowest gradient, where the steepest point, like the steepest slope is. Take a step, and you just kind of keep stepping over this again and again and again. Okay. So So let's do we're kind of this is like the algorithm in action basically. Okay. So let me kind of explain this graph to you just so it doesn't seem so confusing. Okay. So what this graph actually shows is that if I take any two parameters, theta naught and theta one, in your simple linear regression, this is kind of what the cost should look like. Okay. So like let's say if I have let's say if I have my theta naught as one and my theta of x theta. Let me say that again. If I have my theta naught as 1 and my theta 1 as 0, so if I'm looking at, oh, God damn it. If I'm looking at this point here, the cost should be like about 0.2. God damn, I keep clicking. If I'm looking at this point here, so there's like kind of like the minimum point where your cost is like the lowest point. That's kind of what you're aiming for. This little divot here and this little like hill here. This is kind of what we're aiming for because that's the point where the cost function is the lowest. Okay. So that basically means that those are the points where our the line that we've drawn is best fitting to the data. Okay. So either of these 2 points work. If you kind of have a look that this point here, which is at it's 0.4 and 0.8, is kind of like a better fit for the data, but not by a lot. Like if you look at this point here, this is only just a little bit smaller. Like just the cost is just a little bit less, but there's not too much of a difference. So we ideally want to get to either of these 2 points. Okay. So with this man on this hill, and we're at this like start place here. Okay. So we kind of see that the downward sloping is kind of in this direction here. So we take a step here. All right. We take a step here. Next, we stop, reevaluate, and kind of see that the step to take is in this direction here. Okay. We take another step. All right. Sorry for the different sizes. I kind of just copied the graphics from somewhere else, and the sizes and they aren't consistent. All right. So this is kind of glitchy. It looks weird. But we take a step here, take another step in this direction, another step in this direction, another step. We kind of skip 2 steps. Okay. And then you take 2 steps, and you're finally at this bottommost point. Okay. And when you're at the bottommost point, you're satisfied because like you know that this is like the most correct answer you could be. Okay. Yes.
Are we using the algorithm to do that?
Yes, that's the algorithm in the work, basically.
How would we handle getting to a deeper point?
The other point there.
Yeah.
That's actually good. That's exactly what I was going to discuss over. One of the problems with this algorithm is actually the fact that because if you have a look here, let's say instead of starting here, I started a bit more to the right. Okay, just a tad bit more to the right. Okay, let's say like the initial parameters are normally just randomized. So you can normally just randomly pick any 2 parameters, and the algorithm will work from anywhere, basically. But one of the catches, one of the problems with this algorithm is that, let's say if I didn't start from this point, let's say I started from somewhere here, okay? You can kind of see that the point that is actually close, the deepest point that is closer to this point here is actually this point. So if you actually run the algorithm from this point here, you see the algorithm will kind of step like this, and it'll actually end up at this point here. It won't get to like your actual minimum here. So that's actually one of the problems with this gradient descent algorithm is that it can kind of get stuck in what we call local minimas. Okay. So this is like a math thing which you'll probably learn in 1052 if you're not already aware of it. But this point here that we have is what we call a local minima. So and this point here at the bottom here is kind of what we call the global minima. Okay. So this global minima is basically the minimum value for like the minimum value of the whole function. This local minimum is kind of like it's a value that's smaller than anything around it, basically. Okay, so that's actually one of the problems with this gradient descent algorithm, and that you can actually get stuck in this little point here, which is not actually where you want to be ideally. Okay, ideally you want to be somewhere here, but like you may get stuck up here. Okay, so the way that we normally fix this issue is that we kind of run this algorithm like 3 or 4 times with different parameters each time. Okay, and the hope is that if we're going to run this algorithm 3 or 4 times, or like however many times we decide to run it with random parameters at the start, we'll eventually start at a point where we can actually get to this other minimum. Okay, so like let's say the first time we run the algorithm, the starting parameters are actually here. Okay, we run the algorithm and we kind of end up here. Let's say the next time we kind of start and kind of here, so it's a bit of an awkward place to be. And we run it again. It takes a bit of time. We kind of zigzag around, and we kind of end up here again. Next time we run it, let's say we start here, okay? Kind of zigzag here, and we kind of actually get to this exact point here, okay? And then we run it a 4th time wherever we end up. Okay? It doesn't really matter. So we kind of have a look, and we keep track of what the initial parameters were, and we kind of keep a track of what the cost function is at the end of our like 1,000 iterations or how many iterations we want to run. Okay, and we look at whatever the lowest cost parameters are, and we kind of just take those. Okay, so that's one way to kind of combat this issue of the fact that it can get stuck in places which aren't actually the global minimum, so which aren't actually the lowest cost it could be. Okay, that's kind of like the intuition behind the algorithm. It's kind of like this is kind of like the algorithm in action. So each step we take is an update of the parameters. So let's say at this point, I'm just kind of guessing, the parameters look like they're 0.7 and maybe 0.5 or something like that. When you take a step in this direction, the parameters are updated. So the parameters are now like 0.6 and the parameters are now 0.6 and like 0.5 still. Okay. If you take another step, the parameters change to 0.6, 0.5. Okay. So each step that you're taking is actually the parameters themselves changing. Okay. And eventually at this, we'll get to this point where the parameters are like 0.4 and 0.8. And that's like the point where we want to be. Okay. The next step, the next important thing to note about this algorithm, let me just go back to this diagram. It's actually easy to explain. Let's say think back to like you're lost on the hill or mountain and it's dark and foggy at night. Okay, and you want to get home. You want to obviously get home as quickly as possible. Okay, so you have two options, but you start to take like really big steps. Okay, you kind of take a really big step downwards. Okay, revalue your position, take another really big step downwards. Okay. Now, in the hope that you will get to the base camp quicker. But the problem with this is that if your steps are too big, you may actually miss the base camp. You may like kind of end up at a place which is not where you want to be. Okay, it's like because your steps are too big, you didn't have time to readjust yourself properly, and you kind of end up at this other place, again lost in the mountains. All right, but you're a smart man. You like smart person. You think about this, and you're like, all right, I don't want to take steps that are too big. Let me try taking little steps. Okay, now instead of taking like a giant step, you kind of taking like this like 1,000 little steps. Okay, now the problem with that is that by the time you reach the base camp, it will be like morning, and you may be dead by that point. All right, and that's not what we want to be. All right, so if the steps are too little, the thing is that it may take way too long for the value to for you to get to your base camp. Okay, so we need to normally choose step sizes that is optimal. Okay, so it's kind of what this slide basically says is that if the steps are too big, then the gradient descent won't actually work, and you may actually end up missing your minimum, and you may some weird stuff may happen, like the cost function, as I was explaining before. Like you may actually see that the cost function starts to increase if your step sizes are too big. Okay. Obviously, if your step sizes are too small, it may take like way too long for you to converge to like the minimum. Okay, I mean, there's no problem with having the step sizes too small, but it's just you'll have to run a lot more iterations. And I mean, you want to try avoid that as much as possible because the data sets that we're using are pretty small, but the real life data sets are only really massive. So even doing one iteration takes a long time. So you don't have to do like a million iterations just because you decided to be extra careful with the algorithm. Okay. So Arvind will kind of go over some like what the ideal step size should be. Normally a good value to take is 0.01 as like a starting value to kind of see how it's going. And then you can kind of reevaluate and run the algorithm again if you think it's too small. And then like you can maybe like triple it, like 0.03. Or if you think the step size is already too big, you can kind of half it or like a third of it or something like that. Okay. So that's kind of like you kind of have to use your own experience, like your own judgment with this kind of stuff. So this is the actual algorithm in like this technical parameters, fancy terms. Okay, let me just kind of explain the algorithm. So this theta j is the parameter. So what this algorithm is actually showing is that if you want to update your parameter, what you do is you take this parameter and you take away this constant that we've defined called alpha, and this is the step size which I was explaining before. Okay, alpha times this is just fancy symbol for the partial derivative. Again, if you guys don't already know, if you guys don't know this right now, you'll learn this in 1052 stuff later on. So this is basically the point. The point of this partial derivative is that it shows the direction of the steepest descent. Okay, so this basically shows that if you take a step in this direction, this this will help you get to the minimum the quickest way. Okay. So that's kind of what this, that's just like a fancy way of just saying that if you want to update your parameters, you just take away the step size times by the steepest slope value you can find. Okay. So this is kind of like your derivative. So partial derivative is kind of like a derivative. You may have done derivatives in high school, but it's like a fancy type of derivative. This jump from here to here, we won't cover the math side of this because it's a bit, it's hard to see why if you haven't done the derivative stuff. If you are interested, we can kind of discuss it at the end of the lecture, at the end of the workshop. If you are interested in how we got from like this slide, previous slide to this slide. Okay. So this algorithm, I'll kind of just explain this. If you want to update this data naught parameter, so this is the same as like your C parameter, like your y equals mx plus c. You just go alpha times 1 on m, and again, m is the number of training examples we have. And the thing you're trying to, and then you have to do the summation again, and you're basically trying to sum over the difference in your actual values. So difference in like your predicted output and your final output. Okay, and you just kind of sum over that. So if you actually if you kind of go over this example here, if you want to update your theta naught parameter, what you do is you take this E1 plus E2 plus E3 plus E4 plus E5, sum all those values up, and divide it by m and times it by alpha stuff, right? If you want to update this theta 1 parameter, it's almost exactly the same. However, there's this little extra xi term there. So what this actually means is that after you figure out the difference, after you figured out the difference between your predicted output and your actual output, you need to times it by the x coordinate of your example, and then you can sum over that. Okay. It's like the reason for this is due to the derivative stuff, which again we can cover at the end of the stuff if you're interested. Okay. So that's the simple linear regression. Simple linear regression just means it's two variables. The multiple linear regression stuff isn't actually much more different. It's just you can't visualize it anymore because like it's like obviously it's not 3-dimensional or like 2-dimensional anymore, so you can't visualize the actual answers anymore. Okay, so I'll just let me just go over some notation real quick before we get into it. So normally before we were just using the superscript I in brackets, but now we have this little j notation as well. Okay, so normally how it works in multiple linear regression.
Lining up a fucking way too smart, bro. Oh, you should probably mute.
Someone's someone unmuted real quick. All right, so in multiple linear regression, that there's normally multiple features that we have. So like if there was like size of house, you could have like the size of, if you want to predict the price of a house, you could have size of a house, area of the house, number of bathrooms, number of garage, etc. Okay, so that's why there's like multiple features, and that's what a feature is. It's basically basically like if you think about it, a feature is basically what's changing. Okay, kind of like your independent variable. Okay, in the sciencey sort of terms. Okay, so XGI basically just means it's the value of the jth feature in the ith training example. So if you're given a data set, normally what that means is if you take the ith row and the jth column, that will give you this value. Okay. Xi is basically the column vector of all the feature inputs. So basically what this means is that just kind of take the whole row of your ith training example, like just take the ith row and that's what you will get. Okay, so that's Xi. M is the number of training examples, N is the number of features. Okay. So the equation for multiple linear regression doesn't look much more different. It's just that there's more parameters. So there's x, theta naught, theta 2, theta naught, theta 1, theta 2, theta 3, all the way to theta n. And even the inputs are x1, x2, x3, all the way to xn. Okay. Again, same sort of thing. Y hat is the thing you're trying to predict. Theta naught, theta 1, theta 2, theta 3 are the parameters you're trying to vary. For an example of this, if you want to think about it, theta 1 is kind of like the price of a house. Let's say, again, this is all price of a house. You're predicting the price of a house. So theta 1 could be the price of the house in square meters. Theta 2 could be the price per floor. X1 is basically the number of square meters of your house. X2 could be the number of floors of your house. X3 could be number of bathrooms. X6 could be like how many garages you have. Because like all these factors influence the price of the house. It's not just one thing that depends that influences the price of the house. So that's where this multiple linear regression idea comes in handy. Last thing, one more thing, the cost function doesn't change. The cost function doesn't change with multiple linear regression. It's the same cost function. Last thing is the gradient descent algorithm is kind of the same. It's just be careful of this notation here. So xj of I basically. Okay, so basically what this saying is that if you want to update like your sixth parameter or something, you basically need to times it by the sixth, value of all the 6 features, and in the ith training example. Okay, so it's kind of hard to explain what this means, but once you kind of look at the code for it, it'll make a bit more sense. All right, that's it for the multiple. That's it for the linear regression. Are we going with the practical stuff right now? Or are we
doing practical
stuff? All right, we're gonna do the practical stuff. All right. I'll then take over. So we'll just kind of go over simple. We'll just use a simple data set and kind of go over how you code these algorithms up in Python.
Okay, so this is linear regression with one variable. So it's just an x and y. See that? That's too big. All right, so as usual for all data science, we got to use NumPy and pandas. So the data set for this one, we're going to be using something called the salary data set. So basically, it has a column for the years of experience and the salary a person gets. I don't know what industry this is for, but that doesn't really matter.
I need to stop this pinging for Slack. Hold on. How do I stop Slack from like notifications?
Just exit Slack.
Can I exit Slack? Does that work? All right. Nice.
There we go. Right, so that's basically like the first 4 columns of how the data looks. Right, so now we got the hypothesis function. This is the H theta function that you were looking at just now. That's basically, what's the variables you used? I can't. Yeah, well, but that's basically the y-intercept, and that's the gradient of the line that we're dealing with, if we're talking in terms of linear algebra. And that's the cost function over there. Can you?
Yeah, I don't know how to.
Just quit, right click.
Yeah, quit. All right. No, you're not quitting? All right. Quit.
All right, it's fine.
Oh, there we go. Should be it.
Okay, so the cost function here is just a straight up implementation of whatever the formula was. So this m here is the number of, so basically the m here is the same thing as before, is the length of our data set. And we're just summing over all the not mean squared, sorry, we're just getting all the square errors here. So this is the actual value and this is the predicted value. And we're summing that and then we're dividing it by 2n. And this is our gradient descent function. Again, a pretty straightforward implementation of the formula. So this is going through the iterations that we're dealing with. How many iterations do we want to train for? And your hypothesis, here's theta 1, is being calculated with the same formula. So this notation basically says, subtract from theta 0 this value. And for theta 1, we're calculating with the multiplication of x. Again, a very straightforward implementation of the formula.
Wait, actually, one note with that stuff. If you actually have a look carefully at how Arvind implemented it, he actually calculated this h of x first, okay? And then he subtracted these 2 values, okay? An incorrect implementation of how you do this is like calculate this, subtract theta naught, and then recalculate it again, okay? The reason why you don't want to recalculate it again after subtracting theta naught is because your parameters have changed. So like your predicted values would have also changed, okay? So you don't want to do that. So this is like it's a very tiny little point, but it will help make your run your algorithm right the first time around. So that's why I just calculate as Arvind has done here, calculate the h of x before you do any of the subtraction stuff, before you actually run the gradient descent algorithm. Okay? All right. So I should mention that.
Right, and then we're calculating the cost of, so like basically our error, the one we got up here. And then we're appending it to a list so that we can see how our cost looks over our training period. Now this predict function basically combines the whole process together. So we're calculating gradient descent, and then we're doing predictions. Okay, so Oh God. Oh, it's training. Okay, it's fine. Okay, so we got our thetas.
I'm sorry. I'm sorry.
Why does this happen when I'm presenting? Right, so this is our theta naught, and this is our theta 1. And now we're just going to plot everything. So the blue dots here are the data, and the orange dots are our predictions for the given input feature. And in our case, the input feature is the years of experience. Right. And this is our cost function down here. And you can see that over our training period, cost function gradually decreased to 0, which is a good thing. And at some point, it stayed at 0, which is probably when we should have stopped training. Right. So that's just linear regression with one variable. This is linear regression with multiple variables. Now, this data set I'm using has no context. It's just numbers. I tried using one with context, but it wouldn't work. So anyway, so that's basically how the data looks. We've got column 0, 1, and 2. The column number 2 would be our prediction, or the y values. And the 0 and 1 would be our input values, which is x. Once again, we're getting the length of our data set. Now here what we're doing is we're adding an extra column here. I'm pretty sure this is for bias. And then we're calculating some, actually no, you can ignore that, that's just me testing stuff. So this is assigning our what do you call it? Our output values. So we're assigning the third column, which is this guy, to the output, and then that's just basically how the output variable looks like. And this is the input variable, which is 3 columns, ignoring this one here. And now here we're scaling our input values because they're very large here, and Python hates large numbers. Okay. And now we're defining our theta, and we're initializing it to be 0 when it starts off. And then we need this. Actually, we don't need it. No, we don't need that either. Okay. Right, so we're back to our hypothesis, or the h of theta function. And again, it's just theta, the vector, times the x vector, which is returning our value. So that's basically the dot product. So now we have the cost function. And it's also pretty much the same thing as we had before because, they both use the same cost functions. And then we have the gradient descent function. Now this one's a bit different. We can see that for every feature of our input, we're calculating a separate theta, and then we're multiplying it by the entire feature vector, and we're getting we're dividing it by the length of our inputs. Right, so now, okay, so it's more relevant to this one. So this variable, this number here, is our learning rate, or training rate. And 0.05 is pretty good value. I don't want to kill my computer, so it's not going any smaller. And this is the iterations for which we're going to train for. For the sake of this thing, I'm going to turn it down, like go slow, like smaller, because it takes a very long time for this thing to compute at 10,000. Oh wait, we don't need all this. Okay. So this is our cost function down here. Oh god. That shouldn't have. Oh wait, no, it shouldn't have. There we go. Yep. So that's our cost function, and it's stabilizing at 40,000, which is not good. I didn't go through this part. Don't. It's fine. Let's actually try a bit more. Oh, I have to run it from the top again. There you go. Now it's getting better, but it's still like pretty bad. But basically, you can see that the less iterations you train for, the worse your predictions are going to be. Like these red dots here, they are predictions for this data set, which is the blue dots. They're not that great, you know, but the more iterations you do, and I guess the smaller step size you choose, the more accurate these predictions become. But at some point, you're going to level off. You're not going to get beyond a certain point of accuracy, which, you know, is bad, but still. This is just a mathematical model. It's not an actual representation of reality. Okay. I'm going to hand it over to Harsha to. Oh God, no, don't do that.
Does everyone understand that stuff? Everyone doesn't understand the.
Yeah. Any questions?
Yeah. And then, we'll put all this code up on GitHub as well.
Yes.
Yes. So you can kind of have a look at it later. At your own time, at your own pace. Just to see if it will make sense.
I will also make sure to add comments. I did this sort of last minute, so.
Yeah. Comments. Just make it easy. Yes, that will be an email. We'll send it out after this.
Yeah.
All right. So just kind of branching off from linear regression. So I'm going to be talking about logistic regression and kind of at first explaining like what it is and then going into like a few examples. And then we'll have again like a bit of an implementation of it. So just starting with like a bit of a definition, it's like logistic regression is just a type of regression that involves binary outcomes based on independent variables. So it's basically when an event happens or it doesn't happen and you assign it 1 or 0. And there's like different types of independent variables which are like listed there, but basically continuous or discrete variables. And there's like also a few assumptions to be mindful of in logistic regression, like it's a log-based model, so it'll be between 0 and 1. So unlike linear regression where you can basically model anything because it's like negative infinity to positive infinity, it have to be mindful like if you're modeling things like temperature data in like the negative numbers to that it might not be as like the best one to model with. But there's also like a few other assumptions which I'm kind of going through. So the dependent variable should be either binary or dichotomous because as I said, there needs to be 2 categories. And there shouldn't be any multicollinearity between the independent variables. And this is because the natural log has to be related to the measurement variable. And yeah, what's your question?
Would that include or exclude a bimodal dataset?
Sorry?
Would that include a bimodal dataset?
I think no for that circumstance, but I think it'd be like on a case by case basis. Okay. Yeah. And then so does that kind of clarify a little? So just kind of moving on. So with the independent variables, they have to like be linearly related as well. Okay, and this is I'm kind of just going over like how we're going to use it. So in terms of, there's 2 types of variables that logistic regression needs, and one is a nominal variable, which has the 2 values, and one is the measurement variable. So that's like, I've given some examples like for nominal male, female, or like for measurement like time or weight, it's like a continuous variable that you can measure. And kind of the goal is of this sort of modeling is to kind of find if variation in measurement variables causes a variation to like independent variables. So basically if there's a like an event happening or not happening, does the independent variable change or not based on the event happening or not happening? So it's more like a predictable thing rather than finding maximums and minimums because of the range and a bunch of other factors. Just this is kind of the basic regression, linear logistic regression formula, sorry. So I'll just kind of quickly go through it, and the general form is, as you can see here, and this kind of model, the B0 plus B0, like it's not B, but like the X1, X2, all of this is sort of kind of reminiscent of the linear regression stuff. It's kind of the MX plus C sort of a thing, and you have that against the log, and like this is the odds, which is a little bit different from the actual logistic regression formula. So the logs is like probably not the logs, the odds is the defining factor of log regression, and that's because this determines like probability of an event happening. This determines the probability of an event happening or not happening. So if it's like the number of fish in a pond where the sea in the sea where the sea level is at a certain certain like depth, there will usually be a probability. So like if it's shallow, maybe there's not as many fish, and if it's deep, there might be more fish in the lake or sea or wherever. So that's kind of how it's kind of giving context to this model. So it's like if the environment or other factors affect like the probability or the odds. So yeah, just keep a note in your mind, because I'll be going over in the examples that odds are definitely way different to logs, to this log formula. It's just the odds are used to like kind of predict in this model. Yeah. So this is the first example. It's by this researcher from Japan. And like, I'm just gonna go over some basics and ask you guys a few questions. So feel free, if you're on Zoom, type in the chat about what you think your answer would be. If you're in person, feel free to yell it out. So this experiment was basically a bunch of wolf spiders were found in Japanese beaches, and basically the point was to measure the like sand grain size, like one sand grain size, against the like presence or absence of the wolf spiders. And basically this researcher came up with this hypothesis, which is like I've written in the form of a question. So so is there like a correlation between the presence and absence of the spiders versus the sand grain size? And I'll explain why this is relevant like later on. But yeah, that's just the data set. And based on this raw data set, you might not be able to answer the questions, but just give it a go. These are the questions, and it's just asking which of these variables is like the nominal. So that would be the grain size versus the spiders present, and which one is the measured one. And do you predict that the sand grain size would affect the presence or absence of the spiders? And like, why do you think that? So I might give you guys like, 30 seconds to come up with an answer, and then I'll kind of explain it. But this is the data set. What? It's so bulky. Yeah, no, it's not gonna fit. I don't need it.
Just pretend you're standing.
Yeah.
Hopefully.
Okay, so does anyone in the chat or in person have answers? What do you guys believe what do you guys believe the nominal variable is, and what do you think is the measured variable? Okay. All right. Okay, Okay, so I'll just kind of explain the second one a bit further, but the first one, obviously the nominal variable is whether there's going to be spiders there or not, and the measured variable is the sand grain size. So I think the second one I'll kind of go through if it does or does not affect if the sand grain size does or does not affect spiders being there. Okay, so this is a bit of a big slide to take in, but it's just kind of detailing the step-by-step process that like modeling programs, like I used Excel for this, but a lot of modeling programs take to kind of calculate logistic regression. So I'll just briefly explain it and then I'll go in more depth in like a few slides. So basically you have to calculate the probability of the spider being there or not. So obviously it's a probability, so it has to be between 0 and 1. And that's kind of to do with the odds of the spider. So that's how that sort of comes in. And then the second step is to calculate the odds of them being there with this equation, which is kind of like listed over here. And then you use y, which is the calculated probability in step 1. And I'll go over like the difference between the probability and the odds, which is like a little bit confusing. And number 3 is just to find the slope and the intercept via this equation. So earlier on in the logistic regression, like formula slide, it was kind of, like B1, B2, like beta 1, beta 2, all of that. But you can represent it like, like in the y equals mx plus c form. And this particular study used ln, like natural log. But yeah, like log of base anything can be used. And then after that, the program usually computes like via the maximum likelihood method, how many iterations to find the best like line of fit. Typically, because this data set is pretty small, it will be like, it was 20 or 30 from what I read, but it's usually a lot more because you need to do many iterations to find that sort of a best line kind of a fit. And then you, after this is the equation that kind of came out of it, and you just have to rearrange for y, so you can basically input any like sand grain size you want and find out the probability of a spider being there or not on any beach. Yeah, so the first step is calculating like the probability of spiders being there or not. So I've just kind of quickly shown how that is. It's pretty basic. It's just the like data points, like the number of times present was repeated in the raw data against the total. So that's how I've done the same thing for present and absent. Yeah, so I basically went to this one, I counted those up, and then I would put these values in the odds expression, which is step 2, to find out the odds of the spider being present and absent. And basically the odds is like the likelihood, if that makes a bit more sense. It's like the likelihood of a spider being there. So like 2 in 1 odds of the spider being there. And then same thing for being absent. So it's like quite a small value, so it's not as relevant in this context. And then the third / the fourth step is to kind of find the like line of best fit. And for this one, like not many iterations were involved. And it kind of went through this general equation and it went through this general equation to like base the model off of. So with that, this is the logistic regression iteration equation, which is basically just what the computer uses to iterate over multiple times. And in this case, it's used like the linear exponent, but it can basically be anything. It could be like depending on the number of variables. So in this case, it was 2, like just the grain size and the spiders. But if it was like a bunch of other variables included, then it would be like, maybe C plus C and things like that. And then this is just, yeah, like I said, the equation that the computer got from that. Yep. So So I skipped a step. So then after that, with this equation, we want to rearrange for y so that we can basically have a model that we can graph to find out like the probability at different, the probability of spiders being there if we have like a given grain size. And that was kind of the point of this whole study, was to find out if there was like a variation or if there was any dependency. So basically for that sort of things in statistics, maybe you might not have covered it yet, but there's this thing called a p-value, which basically is a measure for if your hypothesis or like your question is valued or not, or like null, or you should reject it or accept it. And then I've just listed a few methods here that you can calculate, that you can use to calculate these things. So in this case, because the likelihood ratio and this chi-square method both has such a small value, and the hypothesis is null if it's under 0.01. So this kind of, it's kind of complicated to do that, and I can explain more, and there's like a few references and links that that can kind of help you kind of step through that process. But yeah. And so basically, as I was kind of saying before, the p-values kind of are like explain the probability of getting the like results as compared with like the results that have been observed. So it's just a measure for if there is actually variation. So as we saw in this case, because the p-values were so small, it's not there's not much correlation between the spiders being there or not, which is what this model was actually trying to find in the first place. So because it's so small, this hypothesis should be statistically rejected, but I think that this data is still relevant because of the context. So even if this data wasn't proving if there is variation based on like these kind of events happening in the sand grain size, it's still kind of important to reflect on these, because as these spiders specifically in Japan are endangered, it would be like a great way to kind of fix that problem if there was like a more correlation. So that's kind of the example. That's kind of the reasoning. But the next example is going to go kind of over the a different sort of a thing, and it'll be covering like the logistic graph model, like logistic regression as a graph, and as like a not just kind of the proving or disproving the hypothesis. So basically this experiment was done by this researcher as well. And I'll just kind of skip over to the question, which is just allele frequencies, which are like these biological gene variants in fish and like other animals, are they associated with latitude or not? And that's because they kind of wanted to see like the population, the alleles and the gene variants in the fish. And it kind of goes over two types of genes or alleles, and that's kind of going into like multivariate logistic regression. This is the raw data, and you can take a look, but I'll be asking kind of the same questions where what is the nominal, what's the measured variable, and what do you think the log plot would look like, the log regression plot would look like? So yeah, feel free to have a discussion or like 10 seconds, 30 seconds, and I can give the answer. Okay, so basically, well, the nominal is the which allele. So if it's MPI 90 or MPI 100, like which allele value is there, and the latitude is obviously the measured value. So the p-values in the raw data were actually given to us. So with these values, you can it'll be kind of the variation, like the error, if you can say, for each of the data points. So I'll be kind of going over that in just a bit. Yeah. And then you just do the whole process from before, like the step 1 to step 5 thing I showed like ages, yeah, like this sort of stuff. I just kind of simplified that because it's kind of the same process. So this is kind of the line of best fit for this particular example, and you have to rearrange for y, so you can put in any type of latitude, so you can get if the probability of like this 100 allele kind of thing. And these graphs actually, like, they do result in the same line, so you can use any of the models, but I think that definitely the y one is the one to use, because it kind of reflects the general regression model the general log regression model that I showed earlier. And I'll show you how the graph looks kind of in this next slide. So yeah, that's the graph. On Excel, it kind of looks really messy, so I just kind of drew it out like this. Don't mind the values and stuff. I have the Excel files for that, so I'll just pass those on. But basically, you can see that it's like a S shape. You can't really see it that well, but it's like a bit of a S shape as compared to it being straight. But that kind of characteristic is really important to note, because in certain under certain ranges, it looks kind of linear, which it's not. So it's something that you need to be mindful of, especially for like the multivariate log regression. Yep. So yeah, that's kind of just reiterating what I've just said. So it looks kind of linear between like if x, our latitude was between like these sort of ranges, and then and it looks kind of S-shaped if the latitude's between this sort of a range. So it's really you have to be really careful that the values match up properly. And this is kind of the p-values and the probabilities on the side, which, yeah, these kind of values that you can see on that side. So yeah, make sure that it's really clear which type of graph it is. And yeah, just another note, going back to this equation, usually if you do graph it, be mindful that you really might not see that S shape really easily. So you do have to select a specific range, especially if you're looking for a certain like characteristic or things like that. So that's especially important I found like the multivariable like variate log regressions had that issue the most, but with single variables, like the first example, the distinction was pretty clear. Okay, so this is just kind of going over the key differences, which I've been outlining throughout this whole, whole workshop. But it's really important for the prediction for you to note what the prediction models, assuming the values are. So there was a question earlier about binomial distribution, I think, and I think log regression does accept that sort of stuff, and accept that value, and the log regression really wants like the 2-value sort of model. And then the linear regression will obviously explain before, like standard distribution. Yeah, and then these are just a couple of tools for log regression, and I've just listed them out, but I recommend probably Excel, and that's like, this link is a pretty good starting point. It just has a bit of like examples on how to get started and how to do the iteration thing. And the second one that I really recommend is RStudio Code, because it's specifically for like statistics and analysis. So they have a lot of tools for if you want to compare like linear versus log regression models for like a set of data. It's a very helpful tool. And yeah, there's many more. And yeah, that's the end of the log regression section. We'll be going on to like a bit of a practical example again. So Arvind will be explaining that.
One other question. Could you go back a slide, please?
This one?
Yeah.
Wait,
Back on.
this one?
Yeah. So you can raise through this one.
Yeah, sorry. Yeah, just feel free to take notes if you want.
You guys set out a link to that one.
we haven't sent it out. Send it out. Okay, yes. Yeah, we'll see. We'll put it all in the email. Yeah, there's a lot to cover. So yeah, we have.
Right. So for this demonstration, we'll be using a little data set that collected the health status of a bunch of civilians. So the thing we're going to try and predict in this one is if they have a heart condition, like heart disease. And we have the column here that's like yes and no. So that's basically a binary decision, 0 or 1. And we're going to use everything else in the data set to predict that one column. So the first thing we're going to do is load the data set, obviously. And the second thing we're going to do is actually find all the unique entries within the columns individually. And then we're going to replace them with numbers from 1 to however many unique values there are, because we don't really want to deal with non-numeric data. So we can see, if 1 is predicted, it means the person has a heart disease. If 0, it means they don't have a heart disease. So, and then we add these new columns into our data set, and you can see these columns added here, chest pain and stuff. And then we remove the non-numeric columns, and now they're gone, and now we have everything numerically. So now we're going to set our y variable to the desired output, which is the heart condition, yes or no. And we're going to set the rest of this stuff. Actually, we did that earlier. Yeah, there we go. The rest of the stuff here, this is our actual input variables. We're going to initialize our thetas at 0.5 because why not? Because you can randomly just initialize them. There's no set number. Now this is the hypothesis function, the cost function, and the gradient descent function. So the hypothesis function, we're doing a little, copying straight from the formula. And we're subtracting a little small number here because in the case that we get 1 as our log, as our hypothesis, then at some point during the gradient calculation, you have to do 1 minus 1, which is going to be, in the cost function, that's going to be devastating because there is no definition for log of 0. And the cost function, again, is another straightforward implementation of the formula. Just, Now, in the gradient function, the first thing we're doing is getting our length of our, the size of our training set, and then we're getting the cost value of each step. So this variable j is going to be storing all the cost values at each step of training. Then for our training time, or in each iteration of our training, we'll be calculating our hypothesis, and then we'll be also calculating thetas using, again, the formula that was just shown to us. And then we're storing all our cost values so that we can see how well our training went. And then we're returning the values. Okay, so now this predict function is pretty much doing the same thing as it did in the previous examples. It's just combining everything together. So we're getting, we're training the model, and then we are testing the model. So here we train with a training rate of 0.03 for 3 epochs. And you can see that the accuracy is terrible, 54%. That's awful. Then we train for 20,000 epochs at a rate of 0.01. Accuracy is 66%, still not great. And that's our cost function. You can see it's all over the place. Then we train for 5,000 epochs at a rate of 0.0005, 61%, I don't have the cost function for this one. Oh, no, I do. Right, and it's getting better. It's getting better, but it's still crap. And then we train for 15,000 epochs at a training rate of 0.001. And we get a good accuracy of about 83% is decent. And our cost function is actually starting to look good. It's going to 0. And we go further up in our iterations. We go to 20,000. And we end up with an accuracy of 84% and a good looking cost function. And then, yeah, ignore that. Yeah, 84%. So that's pretty much the highest we can, or I could get to. And that was with training with those.
That kind of shows the importance of having not only the right learning rate, but also like number of iterations. Yeah.
So if you don't go high enough, you'll get a very bad cost function. If you go way too high, it'll take ages for it to calculate. And this is fine when you're working with like maybe 10 megabytes of data, which I was working with. But if you're working with like terabytes of data, it's going to take you hours or even days to compute all this stuff. And so you don't want to go back and realize, oh my God, I used a terrible start. This, about 2 minutes.
Oh, okay.
Because I was using a very small data set. Yeah.
Wouldn't you get like 300 times speed by writing C?
Yes, you are correct. But implementing these algorithms in C is extremely difficult, and I would not recommend it when you start off. I mean, yes, you're correct. C and C++, see, with machine learning, right? When people start out with machine learning, especially in research, they use Python to test everything. Once they finish testing and they actually want to implement a model, they'll go to C++ or some other fast, like on the base level programming language, and they'll implement the model in that programming language so that production is actually fast. But for testing purposes, Python is great enough.
Developing one. Okay.
Yeah.
Cool.
TensorFlow and stuff is mostly written in C++.
Yeah.
You're only writing in Python in C++.
That's one of the libraries we use for this stuff later on.
Yeah, so that's actually the other thing. TensorFlow and PyTorch, all that kind of stuff is actually written in C and C++. So, and even like TensorFlow has APIs for like, not APIs, libraries for C and C++ direct. So you can code directly in C, but why would you want to when you can just do it?
Why go through the pain?
Why go through the pain? I mean, you could if you want to, but still. Yeah. That concludes my part. I also believe that concludes our presentation.
That concludes the workshop.
Why are we clapping?
Congrats.
Congrats.
If anyone has any questions,
Yeah, I think we have 15 minutes or something.
yeah, if anyone has any questions, Zoom chat, if anyone has any questions, feel free to ask them. Pause the recording though. Pause, stop, finish it. Finish it?